right, so we're looking at more examples of linear functions in 3 dimensions. So let's just start off by looking at this table here where we left off, and we've got some table and we want to decide which could represent linear functions. So the idea is if we fix our y values, we should see constant changes in our x values. So let's just make it clear where our x and y values are. So we go up by 1, up by 3, down by 1, up by 1, down by 3. So clearly, as we go down the column here, our y values are not changing by the same amount. Sorry, if you fix the y value, so when y is 0, my x values are not changing by the same amount. Fix y at 1, my x values are not changing by the same amount. And by the same accord, if we fix our x values, let x be 0, my y value increases by 1, increases by 3. So this one, not linear. What about here? Let my y be 0, my x value goes down 4, down 4, down 4, down 4, down 4, down 4. So we see that dz dx is, in fact, linear with a slope of -4, and the change in z with respect to y, let's make sure that that's linear. So fix x, we go up 3, up 3, up 3, up 3. So good. We've got a change in z 3 for every 1. So this one is linear. Okay, so now using these contour diagrams, which one represents a linear function? So first of all, the fact that if we look at this one here, my contour lines are in fact lines. So that suggests that it's linear, and they're evenly spaced. And they need to be evenly spaced so that the same change in y will get me the same change in z. So it would get me to the same the equal increase to a new contour line. And likewise, they need to be evenly spaced so that if I move in the x direction, no matter where I start, the same change in the x direction will give me an equal change in my contour line. So it will give me the same change in z. So therefore, using this idea that, provided the contour lines are lines and evenly spaced, that we have a linear function, it's very easy to recognize that this is not a linear function. Because just most clearly, if we start here, we've got a big jump to increase a contour line from 0 to 2, whereas here it's a much smaller jump in my y to go from 2 to 4. So we have a disparate, let's see, our dz dy is not constant. All right, so here's the last couple questions are just for you to make sure that you get an understanding and are able to do these problems. So pause this video, try to get this on your own. You will be expected to be able to do these problems, after these 2 videos. So take a second to challenge yourself. All right, so like we did in the problem from the previous video, we need to find a place where one of the variables is fixed. So if we look at the first 2 points, we know that dz dx, because my x isn't changing, is 0. And I keep using calculus terms. We're not in calculus. This isn't quite calculus yet. Right now we're just doing 3-dimensional geometry, really. So the change in z over the change in x is 0. The change in z over the change in y, well, my z value is going down 1 as my y value goes up by 2. So we get a slope of negative 1/2. Now we need to find a point where my 2 points where my z value doesn't change. So let's use the first and the third point. So in this case, the change in z over change in y doesn't exist. So my y value is fixed. I made a slight, just as I was talking, a slight um, error. It's not that the slope here was 0, it's that it's undefined. And we can see that because going back to the first 2 points, if we think about what the slope actually is, it's a 0 change in x over a change in z, which is negative 1. So that slope is undefined. So what it means, the fact that the slope is undefined, is that my x was fixed. So similarly, in this point here, looking at the first and the third points, my change in z is negative 4. My change in y was 0. So dz dy for here is undefined because my x is fixed. Sorry, my y, because my y is fixed. So now I'm going to look at the change in z over the change in x. So again, my change in z from the first to the third point is negative 4, and my change in x is negative 3. So I get a slope of 4/3 with a fixed y value. So what would be my equation? Well, using the first point, which is the easiest point, I get z equals 0 plus 4/3 x minus 0 minus 1/2 y minus 0. And just to write that a little bit more succinctly, we get z equals 4/3 x minus 1/2 y. Okay, let's see. So just three more examples. So in these 3 examples, again, same thing. Pause the video, try to do it on your own, and then I'm going to work through these a little bit quicker now that we've had some exposure. So pause the video, try it. All right, so we notice if we look at the first and the third point, my y value is fixed. So if we look at the first and the third point, we can get that the change in z over change in x, z is going up by 2, x is going down by 4. So that slope is negative 1/2. And if I look for the change in z over the change in y, I need to find a point where my x values are fixed. So between the second and the third point, that's true. So if we look at this second and the third point, my z value goes from 0 to 2, so it goes up 2. And my y value goes from 3 to 0, so down 3. So the equation of the linear function would be that z equals, now I need to choose a point. Let's choose this point. They're all relatively equal in terms of difficulty level. So 4, actually no, what makes the most sense is to choose this last point. And the reason why it makes most sense is because my x and my y values are 0. So this is my z-intercept. So we get z equals 2 minus 1/2 x minus 2/3 y. And again, I chose that point because that allowed me to use the equation z equals my z-intercept plus slope in the x direction times x plus slope in the y direction times y. All right, this is a new type of question, but uh, something that I would expect you, a leap that I would expect you to be able to make. So it says that we're trying to find an equation for the linear function that intersects the xz plane given this linear equation and the yz plane given this equation. So when it intersects the xz plane, that means that y equals 0. And when it intersects the yz plane, that means that x equals 0. And what we can get from the information that we can take from this is that in both cases, and it would have to be this way, in both cases, my z-intercept was 4. So let's talk through this. When it intersects the yz plane, x is 0. And when we set y equals 0, we would see that z equals 4. And similarly, when it intersects the xz plane, y would be 0. If we set x equal to 0 in this equation, z equals 4. And it has to be that way because it's the same plane. So we see that the plane goes through the point 0, 0, 4. And in a linear function, the slope is constant everywhere. So if my change in z with respect to x was 3 here, it's always going to be 3. And if my change in z with respect to y is 1 there, it will always be that way. So I get that dz, or change in z over change in y, equals 1, and change in z over change in x equals 3. So we get the equation um, z equals my z-intercept, which is 4, plus 3x plus 1y. Okay, last example problem, and this has to do with just considering our idea of slope. So we've got that z is a linear function with a slope of 2 in the x direction, 3 in the y direction. So take a second to try to get an answer to A and to B. Okay, so for A, it changes 0.5 in the x. And for every 0.5 change in x, we see a corresponding change of, the ratio of 2 to 1 change in z to change in x. So this will be my total change in z from this given change in x, plus minus 2 in the y, or minus 0.2 change in the y, times 3. And this will give me my change in z given this change in y. So what does that equal? Well, this is 1 minus 0.6. So in other words, a change in 0.5 in the x direction will correspond to a change of 1 in the z direction. And a change in negative 0.2 in the y direction will correspond to a change in negative 0.6 in the z direction. Therefore, we get this net change in the z direction. And what about for b? It says if z equals 2 when x equals 5, y equals 7, what is the value of z when x equals 4.9 and y equals 7.2? Well, we could do this sort of find the change in z and then see how it changes. Let's just write an equation. I think that makes the most sense, at least the most sense to me. So we get our equation z equals 2 plus 2 times x minus 5 plus 3 times y minus 7. So these are the points that we're given, 7, 5, and 2. And those are the points that we got here. And then the other values, these were the slopes that were given originally. So it says, what's the value of z when x equals 4.9 and 7.2? Let's just insert those values. So z equals 2 plus 2 times, we're putting 4.9 into here will result in negative 0.1. And putting 7.2 into here will result in positive 0.2. So these values, this is creating my change in z, similar to right up here. So we get 2 minus 0.2 plus 0.6, which is 2.4. So there we go. A handful of examples for you to have some more exposure to linear functions.